Good morning, everybody. Welcome to this Monday, October 12th. We are on week 8, and this is probably a good place to say that we have come midway through the semester, I think. I think we've got 16 weeks of instruction in general, and so this is rightly the middle of the semester. So congratulations on making it through. I hope you are doing well. Good to see you all, and your semester is going fine, is my hope. We're going to continue discussing linear regression, a topic we started on Monday, and we're going to use the rest of this week to complete this topic for the two big reasons I told you last time. One, because it's an important method for problems that are of regression type. Two, because it has got conceptual things that we would need for more sophisticated things that would come in later in other methods. Simplicity is not a bad thing, it's a good thing, and a fundamental understanding of this one is needed. To some of you, the topic is not brand new. To some of you, it may be. And so I've tried to start last time by having to bring everybody on the same page. And for the discussion we will have around regression, and for a good stretch of the topics we are doing on machine learning generally, or statistical learning, if you prefer to see it that way. The book that I posted last time is going to be our reference, and so I'm not going to again and again post it because it is already there in its entirety, and we are in chapter 3 of that book, and so every time I will mention relevant sections from that book as further reading. So we'll carry on this linear regression topic. And I'm going to first remind us where we are. We have completed assignment 4, and I think almost all of you have submitted on time, and it will be graded soon. Assignment 3 is graded and posted, as I mentioned on Friday. Helen is done with that one. For those of you who are, yes? Okay, for those of you who are taking this as 475, this week is when we would report midterm grades. I've talked to Helen. Our goal is to have the 4 assignments, the 4th one, graded, and an average of those reported. That's one option. If we don't get that done on time, then it will be the first 3 assignments which are already graded, and that will be the average that will be reported as your midterm grade. Know it for what it is. It is not going to be a picture that gives you what would have been a midterm exam. This is your performance on the first 4 assignments, or 3 if we don't get to finish the 4th one, and that's what it is. And so you know how much percentage assignments take overall, and so know for what it is. I think you're doing well, generally speaking, as a class in terms of assignment performances, but more things are to come, and therefore I want you to understand that. 575 students, you don't need midterm grade, so you know where you are, and you will get results on. Okay, this is where we are, and today will be the day when you will be submitting your project proposals. I have teamed them up for some of you that needed help, and I'm going to be looking forward to submitting. If you have questions, maybe before we get started, it will be a good time to ask. I'm going to watch out on what you're saying on the chat. But because everybody's now on board, I should not be forgetting asking the warm-up question for the day. Today's warm-up question, the honor of writing it will go to Morgan. Morgan Kelly Rose, you will be typing up the warm-up question. It's a random one. It's a random one, but it has got a connection with what we will talk today. If I fail to show that connection, somebody should remind me later on. 4 or 5 slides into the lecture, the connection should come. The warm-up question for the day is this. What is your favorite ice cream topping? It sounds very random and weird. You will see the connection. It's Monday, it's 9 a.m. in the morning. We are getting fall season now. The temperature is falling down. There is nobody who is craving for ice cream at this time. I know that for sure, but I would like to know what your favorite topping for an ice cream is. Go ahead, participate on that one, and you will see the connection a bit later. Morgan, you're going to type up the question one more time towards the middle, but let people write what their favorite ice cream topping is. Okay, I have set up certain things, and as you might have noticed, I'm eager to start, and so we use all of the 50 minutes we have for the discussion we'll have today. But let me see if there is anybody else got a question. There was one question I saw that said, for the project proposal is one submission, fine. Yes, I want one person to submit on behalf of the team of 2. And it doesn't matter who it is. My goal is to look at through the proposals and approve or not approve. When I don't approve, I would tell you what you need to do to get it approved. For those of you who have submitted one and still are looking for a teammate, I have tried to address that. But if still there are something like that, I would also come back to them. My week is busy this week, but I will make it a priority to go through the project proposals and approve or disapprove or give feedback as quickly as possible, because I want everybody to know the project that they would be doing. And starting from next week, you will actually be doing your projects. And for that reason, it will be a priority. People have hard time to decide are welcome. There is nothing wrong in having multiple interests, and sometimes it's not easy to decide. It's okay. But I think by now you have settled for what you want to do. And if you need to talk to me, use the office hour this week. Once we have settled on a project, I would start by actually talking to each team, at least for a few minutes, 5 minutes or so. So we'll use office hour or some other time that I will arrange where you will have a dedicated time to get started in a way. And so that will be an important thing I need to do with every single one of you, or teams at least. Okay, any questions? I know the chat is busy with very nice ice cream toppings, but anybody who's, you should feel free to unmute and ask, but you can also use the chat section to ask me if you have a question. I remember there was somebody who was trying to speak while I was speaking, and if I interrupted you, if you meant to ask, go ahead. What's the warm-up question? Christopher Roberts is asking. So Morgan, this is the perfect time to type up the warm-up question again. The warm-up question, Chris, is what is your favorite ice cream topping? And you will see why I'm asking that in a second. All right, let's get started. Okay, so what we did last time was look at regression, and we called it simple. We called it simple because we were looking at the case when we are writing a model, a linear regression model, when there is a single predictor, just one thing. But usually we have many of them. And so we had a reason for starting the discussion with a single one, and that was called simple linear regression. When we have many of them, which is typically the case, it's called multiple linear regression. And that's where we will start today. And so the model will look like, so last time we saw there was only two things, two coefficients. Our response, our output is a y, our input is an x, and it was just a single one. And so we used beta 0 to show the intercept, and just x and its coefficient beta 1 to show that that was the slope for the response variable. Now we have p of them, and so we just do add all p of them, and then they become the coefficients for these predictors. And just like we had last time in the simple linear regression case, we have an error term, epsilon, that we add at the end. Before I try to kind of explain this, and it is probably already clear, let me try to tell you back to the advertisement example we saw last time. There were three things. We had money, we were selling, you were hired to be a consultant for that company, there was investment on TV advertisement, newspaper or radio advertisement, and newspaper advertisement. And so we came up with things that we discussed and introduced some important things like p-values, confidence intervals, and r-squared, and things like that. We were just looking at one, and we just picked one of those advertisement media to form our discussion. So if we had three, which is what we have, what we could do, and all we were told was to do how to do simple linear regression. We could have done one linear regression for TV advertisement, one linear regression for newspaper radio advertisement, and one simple regression on newspaper advertisement. And we would have found some things, because we saw from that scatter plot, they were not like equally influencing the cells. And so they were varying. And so those betas we would get for a single one of them would show, and all of them were positive. There was nothing where we say we spent some money on this one, but it actually was hurting us. That was not the case. It was helping, but not the same extent. So we could have done this. We could have completely ignored the other two and then have a simple one for this one, and we would have come up with. That is not going to be a satisfactory answer. Why? First, we're ignoring them. but we should not, because there may be something that would correlate them, something that would make, and we will make this one even more precise, as I have told you last time. There is some relationship between them that we would want to capture. Otherwise, if we take just a simple one, it's as if they did not exist. So for that reason, and because we have not been able to put them in one equation either, and so we've got this one, and we've got three. So when the CEO hired you for a consultant, you're going to give them three equations instead of one. And they are not combined in a way. And that's why we need the multiple linear regression instead of ignoring them. But there is one thing that this one is now doing. We're not ignoring them when these different predictors are all combined into one. In this case, P, our advertisement has got three. And we write an equation, a model like this. We've got these coefficients, we've got the intercept, and we've got this beta 1, beta 2, and beta 3 for these three advertisement media we will have. What we are saying with each one of the betas is, the way to interpret it is to say, this is the average effect on the cells, on Y, of one investment, one increase in XJ, the advertisement we chose, holding the other predictors fixed, not ignored. If we were just to do simple, 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 and then we have these three equations, we would have ignored them. We have not, but we are assuming they're fixed. If they are fixed, this is how your investment on TV advertisement will influence. That will be better one. This is how your investment on radio advertisement will affect. That will be better too. And here is what the third one, the newspaper, would be. So the values would be different. They are in the presence of the others too, but the others are held fixed is how we would mean. That is what this simple linear regression model would mean, okay? So I've said this, I've spoken ahead of myself, and here is how this one would look like when we look at our example on advertisements. Okay, to just tell you the advantage or the correctness of having to look at things like this instead of having one simple at a time is, the book has got an example. The book has got an example, a kind of an exaggeration that tries to show you how people sometimes would arrive at the wrong conclusions. And I'll come to a similar point 1 or 2 slides later, but let me say it right now before I forget my ice cream question. This has to do with something that has happened in a beach, like places like in Florida or California, where people have tried to see the relationship between shark attacks and ice cream sales. And there is data, and you can support it, and you could do a regression. Shark attacks, ice cream sales, and you could find a good positive correlation between this, and then come up to say, okay, now we are going to close all these beaches and we're not going to sell ice creams because they are leading into shark attacks on people, which is a disaster. We don't want people to die. And that could be a conclusion you could draw, except that it is a wrong one, because there is other explanation for it, and the book goes into a little bit of a detail on that. What the story is temperatures get high, not like what we have now in summer, and people would go to the beach and they get thirsty, and so they buy ice cream, and so there will be more people in the beach, and because there are more people in the beach, there could be more shark attacks and people could die. And so the relationship between shark attacks and ice cream was not something that happened on its own, but there was another explanation for it. That could have been captured if you used a multiple regression like this, but it would be hidden and arrive at a completely wrong conclusion if you were to just look a simple linear regression between shark attacks and ice cream sales. Okay, now I have not forgotten, so nobody's going to blame me for my random warm-up question for the day. That is, you may find this one exaggerated and a little funny, but there are people who kind of draw that kind of conclusion and even publish or sometimes mislead in some places intentionally in some ways. Okay, so how do we interpret these regression coefficients when there are multiple ones? The ideal scenario is when there is a balanced design. So I have told you what the beta 1, beta 2, beta 3 means when you have P predictors and you have a linear model. That's a multiple linear regression. And so the way you interpret them is how this XJ, the coefficient of it, shows us the change in Y while those other variables stay fixed. This kind of interpretation is possible when there is no correlation. So it's not just about having to fix them as opposed to ignore them, which is the difference between multiple linear regression and multiple uses of simple linear regression, that distinction. But once you have in a multiple regression one, an interpretation like this, like the one I gave you a slide ago, would be possible when the variables, the predictors that is, are not correlated. But correlation is a common phenomenon. There will be something that is going to be strongly correlated with another one. And so this kind of, when the others are fixed, this is a change will not any longer be possible. And that is because we could have, and we will make this one more mathematical in our third and last lecture on this one, and we'll come back to see something similar later on in the course also, it's important for us to know when there is correlations between variables. Otherwise, our model would be a bad one. In other words, I could have this beta 1, beta 2, beta 3 coefficients for my predictors. And if they are highly correlated, I could actually swap one of these coefficients for another one and not have a lot of a change in my model, because they were so correlated. Whatever it is that I gave to one of the predictors, my xi's, I give it to another one, the same coefficient, I'm not far off. After all, they're not telling me very different things because they are highly correlated things. So what does it mean? Then that means there is a lot of variance for all of these coefficients, and that tends to increase sometimes dramatically, and that will be difficult. And therefore, that type of interpretation becomes difficult in the presence of correlations between variables. People who do regression problems is one of the issues that they deal with something like this. You'll have to uncover them, and you'll have to do more analysis to find out when they are, and be careful about the interpretation, and sometimes also have a remedy for having to deal with collinearity or relationships between variables. Okay, so this is the ice cream and shark coming again, but for slightly different reason. That one was extreme carelessness in a way. You have just left it out, but you could also have a multiple linear model, but not be careful about the correlations, and so you could have a faulty claim of causality, and it should be avoided, is what I wanted to say. There is a quotation that the book doesn't actually probably have it, but these slides have, and it is important to remember this, and it's a good one as one slide, and you can come back and look at it later on, because I'm not going to spend a whole lot of time on it. But there are two statisticians here, and this is a book written in 1977, and Teki, we know him. We know him because we met him when we talked about EDA and visualizations. This other person, we haven't met him, but meet Bostler. He wrote a book along with Teki in 1977 called Data Analysis and Regression. And so I think there is some things about it that is, I mean, I'm not sure if many of you were born, most likely you were not, but people were talking about things like this at that time also. And so this chapter is what these authors of this book quote as a useful kind of word of wisdom to keep in mind. And so there are 3 points in here, or they're kind of supporting one another, but the point is about how to interpret this beta J estimates for multiple linear regression model, what it means when you say, when these other ones are fixed, here is how a change in this would change the outcome when the variables are correlated with one another. And here is a concrete example which you can very much relate to. If you have the amount of change in your packet is y, your y, and you've got two variables, two predictors. One is how many coins you have, and the other is how many pennies, nickels, and dimes you have. You can see these variables are correlated with one another. And so your interpretation of how the coefficients for these two will become important, because one will be very much telling you something that this other variable is telling you. And that's what this example is trying to show you. The second example will be appealing to those of you who like sports, and I know there is at least one or two of you who would want to do a project on sport analytics or something like along those lines. But here is a model actually based on real data, and this is about football. And why the thing that's to be predicted is the number of tackles by a football player in a season, where you have weight and height of the players given, and the regression model for it looks like this. Why? That's the number of tackles equals to some intercept, some coefficient, beta 0. Now it has become just P0. And now look at what the coefficients for weight and height are. The weight is positive, so that means there's more chance for the number of tackles to be higher the heavier the person is. but the height seems to be having a negative one, which means probably it's better to be short to do tackles is what this means. And you've got these ones, but the two are correlated, and so you have to be careful about how to interpret this, especially the one that is of negative coefficient here. And if you were an analyst on TV or something, I think you would probably be careful about how you would interpret this one. But these are two concrete examples on where correlation between variables is a reason for being careful in how they should be interpreted when you talk about multiple linear regression models involving multiple predictors. Okay, how do we compute them? This last time, or last lecture, we saw the simple case. The simple case is you've got an output y, and there is a single predictor, and we decided, or after some looking at math equations, the best way to get our beta, which was just two of them, beta 0 and beta 1. And the beta 0 is the intercept, and beta 1 is the coefficient for x, the slope of the line, was determined by the least squares. The least squares was the one that enabled us to find a line in which the residual sum of squares was minimized. That was how we got to those, computing them. What would happen if we have many of them, when we have p of them instead of just one? The same idea is going to be applied now. So the residual sum of squares now would say yi, the one that I actually got as an observation, and yi hat, my estimate, using these beta zeros, beta 1, beta 2 with their hats. And so that difference squared sum, that is what I want to minimize. And if you plug in the numbers, you will get this. So if you have now this expression that you see displayed on the slide, what are the minimizers? Same drill. I would differentiate this, I would equate it to 0, I find the beta zeros. So this will be the least square estimators, the least square estimators, except that now we have p of them. And instead of a line that we were using when we had just one, now we're going to have a hyperplane. So this equation, if I was, last time I wrote it, because it's kind of fits in one slide and it was not too clumsy, it's not going to be like that. And we don't have to do it, software package do for us. But I want you to understand what these betas, the various betas are doing. And a good way to see it is more with an example, with a visual. I'm going to do this all just for two predictors. It will be very, very difficult to have anything drawn when you have more than two. And so this is called a hyperplane. The thing that you see in green, so the red points are our observations. These are the points. Last time with just one x, and so there was a line. And from that line, we saw those sticking lines coming up and down. Those were the errors, and we added them up. We squared and added them up. We minimized them. And so the one that comes the closest to minimizing those distances was the estimate, beta 0 plus beta 1x. Now we have, instead of a line, we have a plane, and the hyperplane is the better term to use here. And so the idea will become the same. So we are going to find the distance from those points to the planes, add them up, and the one that minimizes, the plane that comes the closest, not to just a single point, but collectively to all of them, is our, this will constitute our betas. This will be the coefficients, and that will be the hyperplane. And this is shown now when you have just two of them. If we have three, then it will be very difficult to visualize, and so we'll stick with two. Okay, so this is how they are estimated, and here is how we will kind of interpret them, how good they are, and what kind of things we will do. You remember the discussion we have had last time when this was just a single one. P-value, or the T statistic was the one that determined us how much of a trust we should put on the betas there, how significant they are in the presence of others is what we will add now. So last time we just had one, and therefore we were saying this is significant or not significant. Now we will have three in this particular case where we are looking at the example with advertisements. And so we have a table like this that focus for a second on the portion that's on the top. This is the place where we are seeing the betas. And that's what the intercept means, beta 0, TV means beta 1, the coefficient for TV. Radio means beta 2, the coefficient for radio, and newspaper means beta 3, the coefficient for newspaper. And so the values are in the place where it says coefficient. So what I meant by, in what I just said, was beta 0, beta 1, beta 2 is what you should interpret TV, radio, and newspaper as. Intercept is beta 0. And so the coefficients for these values, the values of these ones are what is shown in the first column. You'd see those values. And then you've got the standard error, which is what led us into getting the t-statistic and the t-statistic and the standard error together. In fact, it's just the ratio will give us the p-values. So what we are seeing here, the first thing we see here is that when we were looking at just by itself, we remember TV was significant. It had some values. It was something like this, close to 0.046. In fact, it was not far off. And then we kind of see the same value here when the others are present. And the p-value for it is less than 0.0001, which means this is a significant predictor. It has to be there, and it is positive, and the coefficient for it is pretty high, is what it says. Radio has got smaller, which is not surprising having seen the data that we have seen last time. And the p-value for it is small, which also means that this thing is significant. The thing is different now on newspaper. First, the first thing you should observe is that it is negative, actually, the value of it. And the second thing you should observe is the p-value. The p-value is so high that whatever it is that we're going to make about newspaper is not going to be that significant, is what it means. And so TV and radio are significant in predictors here, but newspaper is not. And its impact is actually on the negative. But because the p-value is so high, we're not going to put too much emphasis on what this one is saying. If we were to do a simple linear regression in the absence, now this is in the presence of the other two. Every single one of them is to be interpreted in the presence of the other two, in the presence of the other two. So in the presence of TV and radio, newspaper is not significant, is the conclusion we draw from here. If it were to be just on its own, it would have had, you remember the scatter plot, it would have had some, but not probably a big one. But there is something more that this one is now showing when it indicates that it is actually negative. And part of that answer could be obtained in what is shown in the next portion of this slide, which shows you the correlation between these variables. This is called a correlation matrix. And what you see on the diagonal is something against itself, and so it will always be a 1. And what you see with the cells is the correlation of the variables with the cells, which is another way of saying what influence does it have on the cells. And all of them tend to have some influence on the cells, which is what the scatter plot told us all along. TV had the highest, radio had the second, and newspaper had the third in a way. And you can see those values decreasing, but not like negligible. The TV and radio are high. This is how you see them to the cells. But what about with each other? TV and radio don't seem to have a whole lot of correlation between them. But look, notice what happens between newspaper and, let's see, newspaper and radio and newspaper, through 0.3541. That is very big. And that is part of the explanation why in the presence of radio, newspaper is not significant. That is now coming up from here. You could do now a little more digging here, and because you were hired for that company as a consultant, you could tell them what is happening. It is probably, there is something that the newspaper advertisement was kind of giving you an impression that it is at least helping a little bit. It was because it was done together with radio that helped that advertisement to some degree. That is what this correlation is showing you, and that is what that negative coefficient in the presence of all these other ones is trying to tell you. So your conclusion or your recommendation to the company may be, because this newspaper advertisement is so little in what it is giving, and whatever little it's giving is coming because of the advertisement you have done on radio, it's not really going to be that helpful for you to do any of these newspaper advertisements, and so stick to TV and radio. That will be your recommendation based on what the analysis you've done here and the numbers we have got. So these two things are going best interpreted when they are seen in tandem. The first one would tell you something that would help you, and then the other one will kind of explain it. All right, I have some more important things, or everything that we discuss is important, of course, but I've got a substantial amount of things to discuss. And so I'm going to start by having posing them in the form of important questions to answer about multiple linear regression, and then we're going to go through each one of these one at a time, okay? As a reminder, section 3.2 and section 3.3 in the book is where your further reading will come for this one if something that you need to read more on comes as we discuss. But let me stop for a second, for 10, 15 seconds, and see if anybody's got any questions for me so far. Everything is going fine? Okay. All right. So we're going to look at this question. The first question we are going to ask is, when we have multiple predictors, in this advertisement example, we had 3, but generally we could have many, and that many could be really many in the era of big data and so on. The predictors that you could have, the candidate ones you could have, could really be a lot. Okay, it's not just 2, 3. You could have many things. Is at least one of these predictors useful in predicting the response? Will be one thing that you would want to get a good answer on. So we need some way to assess that. The other one, the other question we want to see is, do all the predictors help explain why, or is it only a subset of the predictors that's useful? This question becomes important when you have many. When you have 2 or 3, you could do something like what I did now, and you can get a more or less complete answer. But when there are many, to know which one is going to help you could be a difficult task, and you need a method. And we're going to talk about methods for doing that. And then how you want to assess how the model does in terms of fitting the data. And the fourth question is, given a set of predictor values, what response value should we predict, and how accurate is our prediction? We have answered some very similar and maybe a larger set of questions when we were talking about simple linear models, a simple linear regression, and when there was only one predictor. And the answers were easy to show about whether it's a good fit for the model. We have used R-squared, and we had used a residual sum of squares and things like that to assess it. I'm looking at question number 3, for example, and whether it was significant or not. We used p-value, confidence intervals, and so on. All of those things went into a single. So how can we extend them when there are many is part of the question. That's how it differs from the questions we asked last time. And because we have many, we better know which ones are good to focus on, which was absent when we had only a simple one. When we had many, which ones would help predict, and how do we choose them? And this is how you should try to get these questions answered. Let's start answering them. Is at least one predictor useful? We used last time to show the significance of a predictor in answering this particular question by looking at the F statistic, and then from it we went to looking at the p-value, right? That was how we came. Now we have many. And so there was an expression we gave for F statistic. This one is not F ratio, and now it's going to be many. And we have now 2 parameters to look into. One is how many observations we have, the N, and the other is how many predictors we have. They should show up. P was absent before, it was just 1. Now we have there, and so because of the presence of P and NN, this is the new metric we will use to find out whether at least one of the predictors is useful. And you can see how they have shown up. And it's probably enough to just see this, and this has got a name, and this is called the P predictors. And when we have N observations, and we've got N minus P, degrees of freedom is what it means. And this is the value that you would get when these parameters are fixed for you. And so you can now see what values you would get for the thing that you see on the bottom, by the way, is a result for our advertisement example, when we have 3 of them. And you can see now the R-squared, which is what we used to show expression, the proportion of the variance explained is what it means. How much of the variance is explained by our model. That's what R-squared measured. We now see, when we have all 3 of them, the R-squared value for our model, for our multiple linear regression model, is 0.897. I'm not sure how many of you are good in memory, but I'm going to guess 90% of you are good in memory. And I am sure 90% of you would remember the R-squared value we got last time was 0.6 something. I don't remember the other ones, 0.6 something. Okay, I think I'm right. I think you would all agree with me. If not, trust me, that was what we got. This is now increased. The R-squared value now went up to 0.897. It was already good. That was just for TV. That was just for TV last time we saw. And I told you, and I convinced you that is a good R-squared value for a problem like this. But now it has gone up because we have taken advantage of these other predictors. That's a good thing. And so we have now at least known that at least one of the predictors is useful, but having known separately what the TV R-squared value gave us, now we are also convinced that looking all three of them at the same time was helpful because it gave us a model that is better in terms of showing that variance. Okay, we answered one question. Let's go to another one. The other question was, which ones are important? And this is going to require us methods that are actually even more general, and we will not have time in this course to look at very sophisticated methods, but we'll look at a few. But let me first give you an idea for what we are after. We are after looking for something that could say, I've got P predictors, and I would like to know which one of these are the most helpful for me. And so you could imagine a situation where you would say, I'll try everything, and I'll try everything and find out what's the best. What is everything? Well, everything means I've got P predictors. I'm going to have a model where I would use just one of them, and I've got P choices. That will be one. I'm going to try, okay, I'm going to pick two at a time, and I can pick 1 and 2, 1 and 3, 1 and 5, 1 and 8, like that, a group of 2. And I'm going to now try a group of 3. Now you can imagine the world you will be in. This is going to be exponential. You've got very many choices. And you try all of this, and you find the one that would give you the best R-squared value, the best B, and so you have assessed the model, and you would say, okay, I've tried everything, here is my result, and therefore this is the model I would go with. You will not have enough time to live. Last time we discovered one sad fact, right? The life we live is 3 billion seconds. 3 times 10 to the power of 9 seconds is all we live. So if we were to do this computation, probably our lifetime would not be enough for a significant, for a P that's like 30 or 40, no way to do that. So that will be expensive. So we'll have to come up with a better way to do. So the direct approach will be exhaustive search. Try everything and find out the band that would give you the best result. And that is going to be infeasible. So here you have an example when P is equal to 40. So what do we do? So we need some automated approach that searches through a subset of these. Not try everything, but a subset, but this has to be done carefully. For computer science students, this is going to bring a lot of things in your mind now. This is not the first time you have encountered a problem that's combinatorial in nature. So you've got, and by all means, you would avoid exhaustive search. There is very little chance in having to successfully solve a problem by using exhaustive. There are times, but that's not going to be the best thing to do. So what you do instead is be clever in what search space you will have. And I said computer science, but at least in other fields also you might have seen something like this. But it is very common in computer science because most problems are discrete in nature, and so they will be combinatorial. That's the world that I come in for the most part. And so you would have to be selective in the space you would search. Optimization does that, right? And so you would have to do your best, and that also presents itself for having to settle for something that's not optimal. So you will be search, you will be doing stuff, and you will be careful, you will avoid having to exhaustively search, and you will settle for a potentially problem that is not optimal, but is good enough. That's where we are headed. And so we are going to look at 2 commonly used methods. The first one is called forward selection. This, by the way, in statistics is called variable selection or model selection problem. And so you are going to now deal with a problem where you have potentially very many models, very many linear models that you could choose from, and you're going to select the one that's the best in terms of having to be a model that predicts in a good way, has got a good R-squared value, for example. And so the first one is called forward selection. As the name suggests, you are going to build this thing forward. You're going to extend it. And every time somebody says forward, you should expect backward or something coming as an alternative, and that is going to happen. So the forward model begins with a null model. No predictor is chosen. So it just has the intercept, beta 0. I've got P, simple linear regression now, that I would add to the model, that I could add to the model if I take one of the predictors one at a time, I've got P, and I've got among these P simple linear regressions, I would add to the variable that results in the lowest residual sum of squares, the one that gave me the best. And so now I have added it. To that model now, I add the result in the lowest, that would add the lowest residual sum of square among all two non-variable models. And I will continue doing this until I don't see any significant improvement in p-value or our residual sum. P-value is maybe a good indicator, and so I will stop. So what I have started doing is now build my model starting from the node model. I added one that has got among the p single variable models, the one that has got the least, and then I have to that one, not to everything. To that model, I add another that results in the lowest residual sum of square among all two non-variables. And so you can see I'm avoiding exhaustive search, but I'm building this in a greedy fashion. I have included one variable, and then I'm going to say who is the best candidate to be added in when this one is there. This is called forward selection. And I'm going to tell you what this one, the appeal of it is. It's good, it's greedy. It is adding something that is only contributing, but it may have the problem of being redundant because of its greedy nature, and we'll try to fix this in a second. But that's the spirit of forward selection. Backward selection starts the other way around. It will start by having all variables in the model. So we are equal, no discrimination here. So everybody is taken in, all the variables are in the model, and now we're going to leave out. We are going to say, no, you're not useful, throw them out, you throw them out. So remove the variable with the largest. When we were in the forward mode, we added the one that has got, that was the best contributor. P-value was used to determine that. P-value when it is high is bad. And so whenever the variable has the largest P-value, it gets removed. And so we do now on the new model we get when one is kicked off, the new p minus variable model is fit, and the variable with the largest p-value is removed, and we continue until we get to a place where we can stop this. This is called backward selection, okay? There is a model selection that is a combination of these two. It's called a mixed one. And the reason you would use it is because of what I told you with the forward, which could be greedy, which is greedy and therefore could have redundancy. The backward one, let me actually go back. The backward one would be useful only when you have p that is not bigger than n, but that can happen. P is the predictors you have, n is the observations you have, how many things you can choose from. The number of cases you have is n. If p is greater than n, you cannot apply this model, and therefore it's not always usable. But you can combine them. You can combine them to avoid the grid and to avoid the reason for having to deal with p that is too large, and that is called a mixed one. But there are others. There are others that would be used other than p-value to find which model has got a good reason for being selected. And this brings us a little bit closer to information theory and the kind of metrics we could use for having to deal with what model to do. Later on in the course, after we learn classification, we'll talk about cross-validation, which has a little bit of closer connection between what to do when you have multiple models to compare. And that is a practical, very, very useful method that everybody should know about, and we'll come back to them. But here is a list of names, and if you need some definitions for what these are, be my guest, look up for them and so on. But the book has got a little bit of indication, but I wanted to just mention the names of these ones for now. Okay, we've got about 7 minutes, and so I'm going to ask you to stay with me, don't lose focus, and consider one other question we have, or one other issue we have to deal with. When we have multiple predictors, it is possible that some of the predictors would have categorical values. And so everything that we have seen so far would give you this beta coefficients that you are associating with the predictors to say they are numerical values. So the increase in this one has influenced my cells by this much and things like that. What if some of these predictors are qualitative or categorical values? How would you deal with them? This is a real problem. This is a real problem people who do with regression problem have to deal with. And so there is a way to deal with it when they are categorical values. So for this example, we are going to look at a credit card data that I will show you here, and the book has got a little bit of details on it. Here are the 1, 2, 3, 4, 5, 6, 7 predictors, and what you see here is how much credit people owe money on their credit card based on these factors. That's what the outcome is, the response variable is. And here is a scatter plot that shows you what how the relationships would know. You know what scatter plots are. Out of these ones, balance is how much money you have on the card. Age is the card owner's age. Cards is how many cards they have. Education is the level of education they have. I don't remember exactly what it was, whether it kind of counts how many years you have post high school or something, but there is some way to measure how educated people are, how much money they make, limit and rating. And I think out of this, there is a few others that are 7 quantitative variables that I showed you and some qualitatives. The qualitative ones, or the categorical values, are gender, whether the card owner is a male or a female, whether they are student or not student, marital status, and ethnicity, one of these. So these 4 other ones are qualitative. And how would you include them in your model is the question. You can, is the first thing to know. And the way you do it is by introducing dummy variables. Dummy variables that would have a 1, 0 value to show the presence of this or the absence of that type of thing. So for example, if you want to capture gender in your model, you could associate a value, xi, that would have a 1 when the person is a female and a 0 when the person is a male. By the way, you could reverse this and you would not have any problem in terms of what the model will ultimately show you. But this is how you would handle categorical variables. Because they don't have numerical value associated with them, you introduce a dummy variable. In this case, there were 2 things to consider. It has level 2, as it is called, and so you introduce a dummy variable that's just 1, and then you could say by having a value of 1 and 0, include it, and then you would have the beta 0 plus beta n, beta 1 xi, when xi now is this dummy variable associated with a categorical value, will have 2 interpretations. One, when in this case, when the person is a female, and the other when the person is a male. And that's how you would interpret it. One way to interpret this one is to consider the one that has got a 0 as a base value, base case, and then the other one will be the difference between that base case and what will happen when the person, for example, is a female compared to a person being a male. That is how you would interpret it. And so in this credit card example, for example, if you were to include this in your model and see what kind of values you would get, fortunately, it turned out, this is a real data set. It turned out that the amount of balance people have on their credit card was not influenced by the fact that the card owner is a male or a female, because the p-value for it was 0.669. So having to introduce this dummy variable I just told you and do everything else that you have to do gives a p-value associated with that variable that's 0.669, which is really, really big. It should be less than 0.05 for it to be significant. That means gender didn't play a role, which I was happy to find out. But this is a real data, and it's probably many years ago, and so I'm not sure if it would hold true in the time we live in now. If you have more than one a categorical variable that has got more than 2 levels, like it was male and female in the previous case, what if you had 3, 4, 5 categories? Well, you do the same thing. You do the same thing by taking a pair at a time, and you will have multiple dummy variables you will introduce. Ethnicity was one of the variables in this particular example that was needed. And so you could have, and there were 3, Asian, Caucasian, and African American, I think is what the data set would show. And there are 3, and so you need to introduce 2 dummy variables, one for distinguishing between one pair, another between distinguishing another pair, and then the last one, which is unnecessary now, will become the case when both of these cases are 0, 0. And so you could introduce that by having, in general, if you have k, a categorical value of these k levels, by introducing k minus 1 dummy variables, you could capture it. And so this data set also could be interpreted the same way that I just told you, by looking at the 1 and 0 values for these dummy variables and considering them as baselines for having to see. And here is the result. This will be my last slide. And I'm only 1 minute away. So this is not a bad place. And you can see what the balance was showing in terms of ethnicity, and see the p-values for this one also, just like the gender case, shows to be significant. And for that data set, The thing that mattered was education, income, and things like that, but not gender and ethnicity. That was what the data set showed and the way to handle them. This was what I wanted to stop at, and we're about time to do. So let me see if there is any very quick question anybody has for me. The last thing I see on chat is Morgan's retyping of today's warm-up question. It's a very nice way to end it. What's your favorite ice cream topping? But I want to see if anybody has got any question for me. If I felt like I was speaking fast and I need to finish, you understand? So we don't want to spend more than this week on linear regression. And so I needed to cover this. I think it went fine, but let me know if there is anybody who's got any question. Otherwise, I think we're done. I think we have passed a couple minutes, so I will let you go, and I'll see you on Wednesday.